This is Amartya Roy, Assistant Professor, Department of Electrical Engineering, GMIT. Now today I am discussing about the topic on three-phase transformer. The topic is open delta connection and Scott connection. So before I going through the open delta and Scott connection, in my last class I have told different transformer connection like star delta, star star, delta delta, delta star, and different vector groups like star delta 11 and delta star 11. Now another two types of connection are there, that is open delta connection and Scott connection. Now first of all we want to know how three-phase transformer is designed. Basically we design three-phase transformer. There is the two types of method. First method is one number of three-phase unit, and another method is three number of single phase unit. If three single phase units, so this is a transformer, single phase transformer, another, this is a single phase transformer, another, that is a single phase transformer. So this three phase transformer, this three single phase transformer, we can combine it and form one three phase transformer. In your laboratory class, when we design star delta, delta star, star star, delta delta connection in our laboratory, that time we use three number of single phase unit, combined it and form one three phase unit. The advantage of this type of design, when one transformer is maintenance out from this three phase unit, either for maintenance or for fault condition, that time two transformers are available. So we can share the load using these two types transformer. But when the three phase transformer, one three phase transformer, then if one unit is damaged, then we cannot perform using other two unit. The total shutdown will be occurred. So this is a benefit. So open delta connection is like that type of connection. So first of all, open delta connection, the criteria is both the side means high voltage side or low voltage side, primary side and secondary side are delta connected. Both the sides are delta connected. Then this type of design occur. Design we can design this type of open delta connection. So why we design open delta? When this type of three unit, one unit is damaged, either short circuit condition or any other condition, that type these two unit transfer power in load. That's why we design open delta connection. So suppose this is a delta delta connection. I am draw a delta delta connection. This is the primary winding of delta side. This is A, this is C, and this is B. The secondary side of this transformer is this. This is A, this is B point, so this is B and this is C, and there is a three phase load is there. So this transformer, this secondary unit is delivered this load, delivered power through this load. So what is the KVA of delta delta connection? So KVA delta delta connection is equal to the unit. KVA is the power unit, so power is equal to root 3 VL IL, that is VL means line voltage, IL means line current, root 3. This is VL, this is I. We can represent L to phase. In case of delta, VL is equal to V phase and IL is equal to root 3 of I phase, we all know. So we can just write it down here. So in IL, we replace the IL is equal to root 3 I phase. So total KVA share delta delta connection is equal to 3, root 3 into root 3 means 3 V phase into I phase. This will happen. But when we design open delta, that means one side, this is a transformer unit, this is a transformer unit. When this is damaged, we can remove this when we design open delta. So that time the picture will be this is A, this is C and this is B. This unit we remove. Similarly, the secondary side, this is A, this is B means this is B and this is C. Three phase load. Now there is no transformer unit because this is, we can replace this, or because this is damage. So this is open delta. Delta means full, this part, and when this is open, that's why we call this type of connection is open delta connection. So KVA in open delta OD connection is equal to VL root 3 VL IL. Now first of all, when this current is flow through this is a phase line current and we convert it into phase current. But in this current, that's only this is the phase current. So in this case, line current is equal to phase current. In case of open delta connection, when VL is equal to V phase and IL is equal to I phase, this is the open delta because there is a single number of current. So this is root 3 V phase into I phase, KVA open delta. KVA open delta root 3 V phase I phase. KVA delta delta 3 V phase I phase. So now I give, this is equation 1 and this is equation 2. Now KVA open delta divided by KVA delta delta is equal to root 3 V phase I phase by 3 V phase I phase is equal to 1 by root 3. This also cancel out. KVA delta delta, KVA open delta. This is the most important term. KVA open delta is equal to 1 by root 3 KVA delta delta. 1 by root 3 is equal to how much? 1 by root 3 is equal to 0.57. 1 by root 3 is equal to 0.57. So, kVA open delta is equal to 0.57 into kVA delta delta. The meaning of this, if this type of delta delta transformer are there, load is, and the load is 1000 kVA. The load is, suppose, the example is, suppose in case of delta delta connection, the load is 1000 kVA. We can supply the 1000 kVA, 1000 kilowatt, anything else, 1000 kVA load. Suppose one unit is damaged, that time we cannot shut down full unit. We can supply through open delta connection, and with that time we can deliver power of kVA open delta is equal to 0.57 into 1000, that is 570 kVA. So, at that time we can share partially 57% load using this type of connection. Using this type of connection we can deliver 57% of load. This is the beauty of this connection. Now, how much load share by this transformer and how much load share by this transformer we can derive. First of all, design the phasor diagram. Suppose this is V AN, this is V BN, and this is V CN. This the voltage through you can, because load is, we can suppose load is star or delta connected, anything else, all are 120 degree apart. Now we assume our load is lagging load, lagging by phi. So that time IA, this is IA and this is phi, lag by 5 degree. This is IB, this is also phi, and this is IC. This is also phi. Now VAB, VAB means voltage drop across this, and VAC means voltage drop across this. So VAB, how can we determine AB? From AN and BN, just we vector addition. Using this vector addition, we can determine this is VAB, this small ab. The angle between VAB and VBN is equal to 30 degree, because phase voltage and line voltage are 30 degree apart. In your basic class, when star delta connection taught by someone, that time they really mentioned that the voltage, in phase voltage and line voltage are 30 degree apart. So, the relation between VAB and IB is 30 minus phi. So, this angle is equal to 30 degree minus phi. Phi is the power factor of the load. Now, we can determine the VAB and IB, and between the cos phi between, or angle between VAB and IB. Now, VCN and VAN, we can determine the voltage of VAC. VAC will like that. This is VAC. This angle is also 30 degree. So, the angle between VAC and IC is equal to 30 degree plus phi, the total angle. And in this case, VAB and IB, the angle is 30 degree minus of phi. So, suppose we assume the power of VAB transformer, that is S1 transformer suppose, but T1 transformer, and VAC is equal to T2 transformer. So, power delivered, power T1 transformer, that means AB coil transformer, is equal to VAB into IB into power cos 30 degree minus phi, and T2 transformer, that is AC, that is VAC IC cos 30 degree plus phi. Using this formula, they can derive some numericals also. So, the main point of this open delta connection, if one unit of transformer is damaged, that time we did not shut down full load. When the transformer is delta delta connected, that time we replace that time we replace the damaged transformer and form open delta connection, and we deliver 57% of power. But if 2 units are damaged or 3 units are damaged, that time this type of connection is not possible. If only 1 unit are damaged, that time open delta connection is possible, otherwise not. So, this is the key point. This is the key point of open delta connection. Now, another is Scott connection. Or TT connection. And sometimes many of say open delta connection means VV connection. V means this is like V, so this is VV connection, and this is called TT connection. The application or the application of this Scott connection is to convert 3-phase to 2-phase conversion. The most important, many MCQ exam in government sector, they ask you above which is 3-phase to 2-phase transformer connection or transformer conversion. that time the answer will be Scott connection. So Scott connection is 3-phase to 2-phase conversion. So first of all, we want to know what is 3-phase connection and what is 2-phase connection. The 3-phase connection, you all know, 3-phase means suppose this is V1, this is V2, this is V3, all are 120 degree apart from each other. V1 to V2 120 degree apart, V2 to V3 120 degree apart, V1 to V3, that is from this side 240 degree apart, otherwise minus 120 degree apart, because we suppose this is clockwise direction. These are 3-phase. But 2-phase, criteria of 2-phase is, suppose this is V1 and this is V2, they are 90 degree apart to each other. This is the first criteria, V1 and V2 are 90 degree apart, and second criteria is V1 is equal to V2. Is the two numbers of criteria. So when we design Scott connection, that time we ensure both the voltage output is 90 degree apart and the magnitude of those voltage are same. In Scott connection, two types of transformer are there. This is the one transformer, another is this type of transformer. This transformer unit is called teaser transformer, and this transformer unit is called main transformer. This is main transformer, this is teaser transformer, and we can get 2-phase output from this side. We can get 2-phase output from this side. The trans ratio of this transformer is, suppose this is N, this is N2. The secondary side of teaser transformer trans ratio is N2, and secondary side of main transformer trans ratio is also N2. The main transformer, trans ratio of main transformer, the full trans is N1, and we bisect by this point, that is X point. So this is N1 by 2 and this is also trans N1 by 2. This point is A point, this is C point, suppose this is P point. So we can supply 3-phase in A point, one phase in A point, another phase is C point, another phase is B point, and we can give 3-phase supply. Suppose this is R, this is Y, this is B, and we can get 2-phase from this end. So this is VA and this is VB. The most interesting, when we assume this is dot, they are also dot. So polarity of this is plus minus, and this is dot. That means this is also dot. So polarity is plus minus. Right? So we can write the phasor diagram. We can write the phasor diagram of this type of transformer, then we give the solution. The phasor diagram of this, suppose this is VA, this is VB, and this is VC. So what is VAB? VAB is equal to, in my open delta connection. This is V AB, this is VC, this is V. This is VAC, another is VBC. They are also 120 degree apart. This is VBC. So just we can write this. Suppose this is, we can take this a reference, that is VBC here, VBC. This we take upper side, V, this is this that is VAB, and this is this that is VAC. So we can from this phasor, so this is BC point, so this is BC point. So similarly this is AC, that means this is A point, this is this point. Are you get it? So this I write here, this is B point, C point, this is A point. So voltage drop across this point, this VBC point, that is this VAC point, VAC. This is, but there is a point X that bisects the VBC. The X is bisects the BC. If the total voltage is suppose 100 volt, then the voltage drop across VBX is equal to VXC is equal to 50 volt. This is my example, because this X point bisects, equally bisects this BC coil. So this is the X point. This is X point. The voltage drop across this point, because we directly connect this is this point. The voltage drop across AX is nothing but this. The voltage drop across AX, because we connect this terminal into this terminal when we design Scott connection. So the voltage drop across AX is nothing but this line. So this is the AX. X, right? Now, most interestingly, this voltage AX and voltage A are parallel, because this is transformer, and voltage BC, the phasor of voltage BC is parallel voltage B, and phasor of voltage AX is parallel of voltage phasor VA. So VA phasor is like this, like AX. VA phasor is like AX phasor. So this is VX. So this is VA, and BC, or phasor voltage BC phasor is parallel voltage B phasor. The voltage BC phasor is this. So voltage B2 phase, VB phasor is like this. So VA and VB are 90 degree apart. This is my first criteria when the two voltage are 90 degree apart. So we can get from this phasor and this connection, we can get from this phasor the VA and VB are 90 degree apart. So this is happened, but we have to ensure the magnitude of VA is equal to magnitude of VB. If we ensure VA is equal to VB, then we directly say this is the chord connection is the 3-phase to 2-phase conversion. So now here I write here for this is n terms, in terms n, this is n2, this full is n1, that means this is n1 by 2, this is n1 by 2 and this is also n2. So the voltage ratio, the voltage ratio VA by VAX is equal to, from teaser transformer, VA by VAX equals to N2 by N. This is the equation 1 from teaser transformer, and the voltage of VB with respect to this is equal to VB by VBC is equal to N2 by N1. This is equation 2. From equation 1 we can write VA is equal to N2 by N into VAX and VB is equals to N2 by N1 into VBC. This is my equation number 3 and this is equation 4. We can write equation 3 and 4 here also another time. VAX is equal to N2 by N VA is equals to N2 by N VA and VB is equals to N2 by N1 VBC. If this is 3-phase to 2-phase conversions, then VA is equal to VB. But we, in back calculation, we give VA is equal to VB, then what happened? Suppose equation 3 is equals to equation 4, then VA is equal to VB, that means N2 by N into VAX is equal to N2 by N1 VBC. N2 is cancel out. So VAX by VBC is equal to N by N1. This is the criteria. For 3-phase to 2-phase conversion. Now, what is VAX and what is VBC? VAX is this and VBC is this, but we don't know what is VAX. So VAX, from this, VAX is how many numbers of turns? VAX is equal to n number of turns. VAX is equal to n number of turns. VA And suppose the VAC is the line voltage. We give the three-phase supply here. It's this point, and this point. So VAC is the line voltage, that is VL, and VBC also line voltage, but VXC is the half of line voltage, because if the voltage drop across BC is equal to 100 volt, then voltage drop across XC is equal to 100 by 2, that is 50 volt, because both are same number of turns. So this is VL by 2. So using Pythagoras theorem, we can determine this AX. So AX is equal to root over of VL square minus VL by 2 whole square. So VL square minus VL square by 4. From this we can write 3 VL square by 4 root over of AX is equal to. So AX is equal to root 3 by 2 VL. AX is equal to. So value of this AX is equal to root 3 by 2 VL. So we can put VAX is equal to root 3 by 2 VL, and VBC is also VBC is the line voltage. So we can replace VBC is equal to VL is equal to N by N1. So this is cancel out. So root 3 by 2 by 1 is equal to N by N1. So N is equal to root 3 by 2 into N 1. So root 3 by 2 means 0.866 N1. N is equal to. So the criteria is, if the main transformer turns is 1000, then desert transformer turns will be 1000 into 0.866, that means 866, and we can connect this manner, and into both the main secondary of main transformer, desert transformer same, then parallel operation will, then Scott connection will happen, and we can convert 3-phase to 2-phase conversion. The application of Scott connection in electric furnace. In electric furnace, the transformer are Scott connected. So this N1, so if this is an example, if the turns, this main transformer turns N is equal to 1000, then desert transformer turns N1 will be 866 into 1000, that is 866 turns. If 866 turns will be there, if N is equal to 1000 turns, this turns is 500, this 500, this N2 and N2 are same, anything happened, and we connect the primary and the second terminal of primary side of feeder transformer in connect with X point, that is the midpoint of the main primary side of the main transformer, then Scott connection will happen. Scott connection will occur, and we can convert the 3-phase to 2-phase conversion. So these are the important topic in electrical machine, where we can discuss about two types of there. First, open delta connection, then Scott connection or TT connection, that is TT connection. In your exam, many questions arise from open delta connection and Scott connection. They can say to design open delta and Scott connected transformer. That time you have to mention this part. And in my next class, I will discuss about the parallel operation of 3-phase and single phase transformer, and we can solve some numericals in single phase and 3-phase transformers parallel operation. This is most vital topic in electrical machine subject. So that's all. If any query, then feel free to contact me. Thank you.